Hello everyone, welcome back. This is a lesson for AP Physics C students introducing some ideas about integration. So integration is when we are finding an area under a function. The calculus process of integration, or finding an integral, is the way in which you can find the exact area under a function. So if you imagine going back to our summer car experiment, if we were to take data every second instead of every minute for the speed of your car, and then we were to find the area of every one of those rectangles, we'd obviously have a lot more rectangles, we would have a much more accurate picture of the actual area. So let's take a look at what I'm talking about there. So imagine you had some function like this. If we were to take data over every minute interval, and then make that into a rectangle, find the area of this box, find the area of this box, and this box. We only have 4 data points. We could find the area of those 4 things, add them together, and use that to approximate the area under this function. But you can see here and here we have holes, and then we have an overestimate here, here, and here. So it's not going to be all that accurate. If we take more data, so we have 1, 2, 3, 4, 5, 6, 7, 8 points here, we get a closer approximation. And the more data points we take, the closer we get to the real area. You can see here that there's not a whole lot of overestimate here, and there's not a whole lot of underestimate there. This would actually work out to be pretty close. So that's the idea. Integration allows us to essentially imagine summing up these areas with an infinite number of boxes. So it allows us to sum up the area of an infinite number of areas over very short intervals. And there's 2 types: a definite, which is with limits, and indefinite, which doesn't have a limit. A definite integral gives us a numeric value because the limits have been identified, so we can get an actual value for the area. Whereas an indefinite integral gives you a new function or formula that can be used to find an area if limits are set. So I kind of think of this like, you think back to geometry. We had different equations or formulas for different areas of shapes. Using an integral for an indefinite situation will give you a formula for the area, and then if you have limits, you apply limits to it, then you can actually get a number. So this is the example of a definite integral. So the way we want to read this is it's the integral of 5x squared with respect to x. You see the dx at the end. That means we're taking it with respect to x between the limits of 0 to 3. Okay, this one would be an indefinite integral. It just says take the integral of 5x squared with respect to x. Okay, so here are the basic rules for integration that we're going to need to learn. All right, so we'll just go through them quickly here. The integral of 0 is a constant. The integral of some constant is the constant times x plus a new constant. And we're going to talk about what these constants of integration are all about later. This one, if you have some function, f of x, multiplied by a constant, then what you can do is bring that outside the integral, evaluate the integral, and then multiply by the constant. That's what this says. This is the sum and difference rule that we saw for derivatives also. So if you have 2 functions added together and you need to integrate, you can just integrate each one separately and then add. This is our power rule. So if you have x to the n dx, to do the power rule, and this is going to be the most common one, you're going to raise the power by 1 and divide by the new power, and then you have plus the constant of integration. So guys, this is the reverse of what we did when we took the derivative of something that was polynomial, all right, or a power function. Okay, the integral of cosine is sine. If you think about, again, this is the reverse of what we learned for derivatives. When we took the derivative of sine, we got cosine. So integration is the inverse process of taking a derivative. The integral of sine is negative cosine plus a constant. The integral of 1 over x is natural log of x. Now this one might not be obvious at first, but if you go up to the power rule, you can see why. If we had x to the negative 1 and we tried to apply this rule, it wouldn't work because we would get x to the 0 over 0. It would be undefined. All right, that's not how that specific situation works. It turns out to be the natural log. And then the integral of e to the x is e to the x. Because it's its own derivative, it's also its own integral. Okay, so here's an example with a constant. If y is a constant, the area under the function is just the area of a rectangle. Okay, so think about if I wanted to know the area under this line, it's just going to be some kind of rectangle. The area of a rectangle is base times height. So in this case, you would have the base, which is whatever the width is, whatever the x interval is, times the height, which is the constant. In this case, it's 4. So the area would be 4x plus a constant. Now again, it might not be obvious to you why you have that constant of integration in there, and I'll get to that in a second, but just think about this. Imagine we wanted to know the area under this function between, let's say, 0 and 5. All right, so you can imagine going from 0 over to 5, it would be the area of this box. So it would be x wide, which is 5, times the height, which is 4, where we get 20. All right, now, why do we need the constant? Well, imagine this graph represents the acceleration of an object versus time. So imagine this says it's accelerating at 4 meters per second every second. And we want to know the velocity of that object. Okay, well, we know if its acceleration is 4 meters per second, then we know every second its velocity goes up by 4. So it could be, 4 meters per second, 8 meters per second, 12 meters per second, etc., etc. However, we don't know, just by taking the integral, we don't know what velocity it started at. Can't assume that it starts from rest. So we also have to add in whatever the starting velocity was. If we started at 10 meters per second, you'd have 10 meters per second at time 0, 14 at time 1, 18 at time 2, 22 at time 3, etc., etc. So that constant of integration is needed to take care of, well, what were the starting conditions? That's why we have to have it. Okay, so here's another example using the power rule. Our function is y equals 2x, so it's just a straight line. If we start at the origin here, the area under the graph would be a triangle. So if you can imagine, if we went from 0 out to, let's say, 2, this triangle would represent the area under that function. The area of a triangle is 1/2 base times height. The base is the x interval, so that's this, whatever x value we have, and the height is the slope times whatever the x interval is, because this is a straight line. So we get 1/2 times x times the slope times x again. So we can write it this way. Area equals the slope over 2 times x squared. If we look at the power rule for integration, this is exactly what we would get. We would need to add the constant in case the function doesn't start at the origin. I said it did in this specific example, but if it didn't start at the origin, we would have a plus c. All right, so what I'm getting at here is if our function is y equals 2x, if we go back, the power rule says this would be x to the 1, really, 2x to the 1, okay? What we would do is raise the power by 1 and divide by the new power. So if we go to this function, right now it's 2x to the first. We raise that to the second power. We would get 2x squared and divide by 2. All right, and if you look here, the slope is 2, x squared divided by 2. It's the same exact thing. Okay. Lastly, definite integration. When an integral has defined limits, we can then get a defined numerical area. Okay. Also, because the area is defined already, a constant is not needed. We don't have to shift anything when we know the limits of integration. So what we do when we have definite integration is perform the integration using the rules. Then you apply the upper and lower limits into the function that you get. And then finally you subtract the lower limit value from the upper limit value. Okay, so using the example we had a minute ago, let's integrate the function 2x with respect to x between 0 and 4. So that's the line that we saw in the last slide. So first, integrate the function and forget about the limits. All right, so if we do that, we get 2x squared over 2, which is x squared. All right, and then we apply the upper and the lower limit. The upper limit is 4, so I put 4 in for x, and I get 4 squared. And I put 0 in for x, and I get 0 squared. And then you subtract the subtract the lower from the upper. So 4 squared minus 0 squared is 16. So the area under that function between 0 and 4 is 16. And I think you could be able to verify that using geometry and skills that you already have. So I'm going to post another video later with some more problem examples using integration, but this was just a way to kind of introduce it.